Hello, all the crazy people out there. My name is Michael. I like wizards and dragons and making games, and welcome back to Screen Space Ambient Occlusion in GameMaker. So this is part 2. In part 1, we set up what you see on screen right now, and I promise it's going to start looking better from here. We've set up most of the infrastructure that we need around the effect, the geometry buffer, the various uniforms and other pieces of data that we need to send to the shaders. And today, we're going to take this scene from something that looks like this to something that looks a little bit more like this. And this is really going to be the meat and potatoes of the effect. This is going to be most of the actual shader code that makes this effect work. However, there is still a little bit more setup that I need to do, and I'm not entirely sure why I didn't do all of this in the last video. Anyway, so before I start, you really should go and watch the last video on this if you haven't already. This is not a beginner level effect. This is going to depend on a lot of bits of 3D math and 3D shader knowledge that you're going to probably want to have acquired elsewhere. I'm not going to be, explaining every single line of code that I write from the beginning. We will be talking about coordinate space transforms, and I'll be assuming that you all know what that means already. In the first video on this, I have linked a bunch of videos where I've talked about all these sorts of things in more detail in the past. So, at this moment in time, we have gotten as far as reconstructing view space position from the depth buffer using this get vs position from source function that we wrote. This is a convenience. We're going to be calling it in a couple of different places in the shader. I probably should have also done something similar for normals. I'm just going to write myself a little function called get vs normal from source. And instead of saying float color depth equals texture 2D samp underscore depth, etc. We're going to say color underscore normal. This is going to be a vec3. We're going to get the RGB instead of just the red channel. This is going to have a range of 0 to 1 on all three channels. We're going to want to convert that return color normal times 2.0 plus 1.0, or minus 1.0 rather. And that's going to convert this normal sample from a texture from a range of 0 to 1 to a range of -1 to +1. This is something we have done many times at this point. And lastly, vec3, let's actually use this view normal equals get vs normal from source. The texture UVs, same as position. All right, so there's still a couple more values that I do need to set up that I haven't sent to the shader yet. And honestly, I probably should have done this in the last video. I don't know why I didn't. I probably forgot. So these four here. So SSAO projection matrix, sample count, radius, and bias. And these two uniform arrays here, U underscore SSAO samples and U underscore SSAO noise. We're going to generate some arrays of random vectors and send those to the shader as well. First, let me go and take care of these, the easy ones. So these are going to be, and all these values already exist. So the projection matrix is just the projection matrix that the scene is drawn with, that we're defining here. The sample count, the radius, and the bias are all values that I have initialized in the create event, as well as SSAO enabled. We'll get to that eventually. Let me see. I'm going to shader set uniform float array, and we're going to do this a couple of times. So the projection matrix is going to be an array, and we're just going to give it the projection matrix that we have used in the draw event over here. We're also going to want Control D, duplicate the line. Have our SSAO radius, and that is not going to be a float array. That is just going to be the SSAO radius value defined in the create event. We're also going to want the bias value that we can get from the same place. And lastly, uniform integer SSAO sample count. So this is going to be not a floating point number, but an integer. And it's going to need to be set as a shader uniform integer, not a uniform float. Shaders are statically typed. You can't just throw different data types around and expect shaders to accept it the way that you can in GameMaker. And also 2 more uniform arrays that I didn't define earlier. And this is going to be a little bit more involved. I'm going to dedicate a little bit more time to these. Let's say SSAO samples is going to be equal to array create some number. I'll fill that in a minute. And SSAO noise is going to be equal to array create. I'll fill that in a minute. I'll actually do noise first and sample second. And just coming back here real fast, let's go and send this value to the shader, SSAO samples. That's going to be a float array, and SSAO noise. This is also going to be a float array. Alright, so let's actually get to defining what these two things are. So, they're both going to be arrays of random vectors. I did not mean to drop a breakpoint there. They're both going to be arrays of random vectors. SSAO noise is going to be 16 random vector 3s, and the way that you pass uniform arrays to shaders, so if you have just an array of floats, that's easy. If the shader expects an array of 8 floats, then you just give it an array of 8 real numbers from GameMaker, and you can call it a day. But if you have an array of a more complex data type, so like an array of vectors, in this case, we're going to be going with an array of 16 vector 3s. And when you send that to the shader, it doesn't expect it to be formatted like an array of 16 arrays of 3 values or an array of 16 structs with X, Y, and Z. GameMaker doesn't know any of that. It's not going to make any assumptions about the data that's contained within this array. It just wants an array of 16 times 3 values in order, because that is the order that the data is going to go into the shader. So 48 numbers in total. You can mentally group them together in groups of 3s, but it has to just be a linear array. And SSAO samples is going to be something similar. It's not going to be 16. I think I'm going to define it as 128. That one's got a little more wiggle room. The SSAO noise, there is a reason for it being 16, and we'll get to that. But firstly, let's actually put some numbers in here. So I'm going to say for var I equals 0, I is less than array, length, len, I hate spelling this, array length, SSAO, noise, I, and I'm going to say I plus equals 3 instead of I plus plus here, because we are going to be iterating over this array in groups of 3. If putting the array length and the update condition in a for loop bothers you, feel free to rearrange this. I don't care. I'm just legally obligated to say that if I don't want to get 50 billion comments about it every single time I do it. So what exactly is going to be an SSAO noise? So this is going to be an array of vector 3s, but the vector 3s are going to be randomly arranged in a disk. So what that means is that we're going to start by generating random numbers. Let's say our random x, random numbers between -1 and +1 on the x-axis, also on the y-axis, but on the z-axis, I'm just going to set the value of that vector to 0 on the z-axis. So these two are not going to be arranged in a disk. These are going to be random numbers filling basically a square on the xy plane. I would like them to be unit vectors with a magnitude of 1 arranged in a circle. And the easiest way to do that is going to be var magnitude equals point distance 3D 0, 0, 0, random x, random y, random z. You could use point distance 2D for this because z is always going to be 0. It doesn't matter. And then we can random x divided by equals the magnitude. Same thing for the y and the z. So now, these 3 numbers represent basically a vector 3, which is located on a disk. And I can actually insert these values into the SSAO noise array. Like this. So SSAO noise index I plus 0 is random x. Index 1 is going to be random y, and index 2 is going to be random z. And we have now gone and populated this array with a bunch of random vector 3s. So next, let's look at SSAO samples, and that's going to be a little bit more involved. So if I go back to the SSAO shader, I have defined macros for both of these. SSAO noise count being 16, like, isn't really that likely to ever change, because as I said, there's a reason I set it to 16. Whereas the max SSAO sample noise count is a little bit more arbitrary. This is more of like 128, I think, is the useful upper bound. So I am actually going to macro this in GML. Max SSAO sample count. Let's make that all uppercase. Like that. And that's 128, and I can go and say that array is going to be initialized to size that times 3, because again, these are going to be vector 3s. And this is going to look similar to the SSAO noise. So we're going to start just by copying and pasting, and then I'll fill in the rest. Like that. The vector 3s in question here are not going to be distributed in a disk. They are going to be distributed in a hemisphere. So if I wanted to distribute these in a sphere, I could say the random z value is also going to be random range between -1 and +1. And now we're going to have a series of vector 3s that are distributed more or less evenly in a sphere. However, I only actually want basically the front of the sphere because the SSAO samples array is going to contain all of the random points that we are going to sample around each fragment, and we're going to use that array of random points, that list of random points that we're sampling, to figure out exactly how many of a fragment's neighbors are like in a corner, how many of the random points are behind something else in the depth buffer, and the more random points that we test that are behind something else in the depth buffer, the more ambient occlusion that fragment should get. And it doesn't really make sense to test points that are like behind you, because we already are pretty sure that those are going to be in shadow. So instead of distributing the random points in a sphere, we are going to just distribute the points in a hemisphere, so half of a sphere, and that is going to sit in front of the fragment that we're testing, and as such, the z-coordinate is going to only have a range between 0 and 1. We are going to be transforming this hemisphere in space so that it's like on top of the surface that is at the location that we're testing. And probably, honestly, most of what we do in this video is going to be doing coordinate space transforms to make that work, but let's not get ahead of ourselves. The other thing we'd like is that I don't actually want all these vectors to be a unit vector. I want them to have a magnitude of somewhere between like 0.1 and 1.0. And once we've normalized it, we can sort of unnormalize it by saying mag equals random range between 0.1 and 1. And we can sort of do the opposite of what we did 10 seconds ago and say random times equals that magnitude on the x, y, and z. And now we've got SSAO samples is an array of vector 3s. And those vector 3s are going to be points more or less evenly distributed in a hemisphere. And the reason that I keep saying more or less is because the distributing random points in a circle or a circle in higher dimensional spaces is surprisingly complicated, and there are more than one ways to do that. I think Numberphile, or maybe it was one of the other math YouTubers, it might have been 3 Blue 1 Brown, did a video on distributing points randomly in a circle and how there are like multiple ways that you can arrive at the same conclusion. And some of them might produce results that are better or worse for the purposes that you're doing. I'll have that video linked in the description, but for this purpose, I'm just going to be going with this because it's random enough and it's also really easy to write. So now, if I run the game, nothing is going to change. We haven't really changed anything in the shader. I guess if you wanted to see something different, I could like go into the shader and write the view space normals to the screen, and this is gonna be incorrect apparently. Did I mess this up? Oh, I'm still sampling from the depth buffer. That's hilarious. All right, let's actually sample from the normal texture because yeah, garbage in, garbage out. So not quite the same as in our normal texture because we are untransforming them so that they have the full range, but close enough. I'm going to go make a commit in source control, and we're going to call this finish setting up the SSAO uniforms, and I think we can be on our way. How am I doing on time? I'm about 15 minutes into the recording. All right, hopefully we can get through this without spending too much time on the whole thing. So I've got our view space normal, I've got our view space position. The next thing I'm going to do is I'm going to pull a value from the SSAO noise uniform array. And the reason that I'm doing this might not be entirely straightforward at first, but I will explain it after I write it. So firstly, let me say, and I guess I could use an IVEC for this, but because it's the GameMaker way, I'm just going to use 2 primitive integers. Integer noise x equals, and you'll have to follow along with me here, integer constructor of modulo division between glfrag core.x minus 0.5 and 4.0. And I think I need to close parentheses there. And integer noise y is going to be the same thing with glfrag chord.y. So glfrag chord is going to be a vector which contains the absolute pixel positions of the fragment on screen in like pixel space, not in texture space. We're going to take the x value of that minus a half just to sort of go in the middle of a pixel, and we're going to modulo division that by 4. The version of GLSL that GameMaker uses currently sadly does not support the percent sign as modulo division, so you have to use a function. Future versions of GLSL and I think HLSL and other shading languages do. But we're going to divide this value by 4, take the remainder, and cast that to an integer. So noise x and noise y are both going to have a value between 0 and 3 in a repeating pattern across the screen. And we're going to sort of use this to seed our orientation of the hemisphere that we locate on each fragment using our TBN matrix. That was a lot of words. So firstly, let me just start with that. I'm going to say vec3 random tangent equals u underscore SSAO noise index noise x plus noise y times 4. And that is just a 4. That is not 4.0 because we are dealing with integers. You could group these with parentheses if it helps you keep track of them. So we are now basically breaking the screen into like 4x4 tiles where each tile is going to correspond to a different index in this u underscore SSAO noise array. And the reason that we're doing this, like, this might look kind of... I'm trying not to say the word random because I've talked about randomness so many times already in this video. This may look a little bit arbitrary, like, why on earth are we doing this? This is because when we place the hemisphere that we're going to sample from on top of the fragment, we want that to be in what is known as tangent space. And the way that we're going to do that, the way that we're going to orient this hemisphere in space so that it's sitting on top of the fragment is going to be using a TBN matrix. I believe I mentioned in the first video that this is going to share a little bit of DNA in common with normal mapping, because we did this when we were doing normal mapping so that we could like orient the normal maps on whatever surface we were drawing so that it behaved correctly when it interacted with light. Here we are going to be using one of those TBN matrices, but we're going to use it to make sure that our hemisphere just sits on top of the fragment. Anyway, let's build our TBN matrix. The TBN matrix is, depending on who you ask, the tangent bitangent normal matrix or the tangent binormal normal matrix. I probably shouldn't use the words bitangent and binormal interchangeably, but I often do. Bitangent sounds cooler for whatever reason to me, so I usually like go with that. But var vec3 tangent is going to be equal to, and I'm just gonna write out random tangent minus the fragment normal multiplied by the dot product of the random tangent and the fragment normal. And this expression might or might not have a unit length of 1, so I'm going to want to normalize that just to be sure. Vec3 bitangent equals the cross product of the actually view normal and the actual tangent vector. And lastly, mat3, so a 3x3 matrix, TBN equals mat3, composed of the tangent, the bitangent, and the view normal. So this is it. We should have done something fairly similar to this in the normal mapping shader, although I think in that case we calculated the actual tangent vector by using the like dy dx shader derivatives. Anyway, let me see. By the way, if you want to see what this looks like, it's not going to look like much if I like write the tangent vector to the screen. It's just going to look kind of like a smoosh. Did I call fragment normal? I keep doing that because in my sample project it was called fragment normal, but I think view normal is a better variable name, so I'm going to be using that here. Anyway, this isn't really going to look like much. Ooh, that actually looks like cooler than I thought it was going to. I thought it was going to be a lot more noisy, but you can actually, because it is in a tangent space for each fragment, I guess, you can actually, like, kind of see a pattern. That's kind of neat. Alright. Should I use that as, like, a video thumbnail? Anyway, now we're actually going to get into the meat and potatoes of the SSAO process. So we're going to now loop over this whole SSAO samples array, except we're not going to loop over the whole array. We're going to just loop over the sample count uniform because we might not choose to use like every sampler in the array. So let's set that up. Gonna drop down a few lines. For int I equals 0, I is less than the uniform SSAO sample count, I plus plus. Hello, I plus plus. So what we're going to do is we're going to loop over our array of random positions, and we're going to sample from a random position close to each fragment. We're going to get the depth of each fragment at that sampled location, and we're going to see, is that depth closer to the camera than whatever's in the depth buffer? If it is, then it's not occluded. If it isn't, then it is occluded. And the more samples around the fragment are occluded, the darker the ambient occlusion is going to be. So given that, we're also going to need to define float occlusion total, and I'm going to initialize that to 0.0. For every pixel that is occluded, this will... Actually, for every pixel that is not occluded, for every sample that is not occluded, we'll increase that by 1. We'll see why I'm going in that direction in a minute. But firstly, I'm going to need vec3. Let's call it vec3 sample is going to be u underscore SSAO samples index I. We can say vec3 sample position is going to be the TBN matrix multiplied by that sample. So right now, the value that you just pull out of the samples array is going to be that hemisphere, and it's going to be like sitting in the positive z, like half of the coordinate space. We're going to transform that into tangent space for each fragment by multiplying that by the TBN matrix, just the same way that we would with the normal that you sample from a normal map. So this is the transformation that's going to put the that's going to orient that sample in tangent space. So we're going to want to transform the sample position from just like a direction vector relative to the sample position. We're going to want to transform that to an actual position in the world. And to do that, we can say sample position equals the view position plus the sample position multiplied by, and I'm going to do this now instead of later, because if I do it later, I'm going to forget. We're going to multiply that by the SSAO radius. So we will be able to later on, like, edit the value of the SSAO radius as a uniform to tweak how it looks. And we're going to achieve that by just multiplying something by this sample position. Anyway, this is now a location in view space. We're going to write that down and save it for later. But next, we're going to have to go through a series of transforms that go from view space basically back into, like, screen space, so that we can sample off of the depth buffer again. And that's because we're going to need to be able to figure out exactly what already exists in the depth buffer at this position. I realize that we're kind of jumping through a lot of hoops to get here, but firstly, we're going to do a few transforms that are more or less like what you would do going from the vertex shader to the fragment shader with the output of GL underscore position. And that is going to look something like, what do I want to call this? Let's say vec4 sample screen space. This is going to be initialized to a vec4 of that sample position on the XYZ and a homogeneous coordinate of 1. So this is already in view space because we've been working in view space, so we don't need to worry about the world matrix or the view matrix. We just need to take the projection matrix that we supplied as the uniform earlier and multiply this by that sample underscore screen space. And I'm just going to go and start recycling variable names because there's already a lot of variable names. And we don't really need the intermediate steps. So this is the this is basically GL underscore position at the end of a vertex shader. And next we're going to need to say this dot xyz divided by equals this dot w. This is the perspective transform, parallel lines converge at a distance, that sort of thing. This is going to put this the sample screen space in a range of -1 to +1. We are going to want to put that in a range of 0 to 1 so that we can sample it from the texture. And now we're going to do the transform that I'm sure you all are getting tired of seeing because we've done it so many times. This dot xy is going to equal this dot xy times 0.5. That's not times 0.5. Times 0.5 plus 0.5. And now, this sample screen space is going to be a vector for the only parts we really care about now are x, y, and that's going to correspond to a position, a UV coordinate that we can use to sample from the depth buffer. So we can do that with the get view space position from source function, and we can just pass that this sample screen space.xy. I'm going to need to think of another variable name for this. What do I want this to be? Vec3. I guess I'll just call it sample in view space equals get vs position from source with this input. This is going to be, so sample position here and sample in view space are going to be very similar values. This is going to be the position of that random sample vector that we use, that we pass in as a uniform, and this is going to be the position in view space of whatever is at that coordinate on the screen already. And again, I realize this is kind of an elaborate way of getting there, but we did all this work so that we can say if the sample position dot z plus the u underscore bias is less than or equal to the sample in view space dot z. So let's go through this again in English. If the sample view space position dot z is less than whatever you sampled from that position, then that means that the random sample that we took is in front of whatever's already there in the depth buffer, and therefore it should not be occluded. And we can say the occlusion total plus equals 1.0. Else, if that is not true, then this sample vector that we took is going to be behind whatever is already in the depth buffer, and it should be occluded. And we can say occlusion total plus equals 0.0. That's a little bit silly. So you could just like omit this if you like. No point in adding 0 to a number. The shader compiler should be smart enough to like optimize that out anyway if it makes it easier to read. So at the end of the day, once you've gone through this whole loop, the occlusion total will have a number between 0 and whatever the u underscore SSAO sample count is. And fragments that have a higher occlusion value will have a lower occlusion total. And in that respect, you might want to like invert this number, swap these values around. Anyway, low number is going to correspond to a more darker effect, more ambient occlusion. A high number is going to correspond to lower ambient occlusion. So I do want this to be in a range of 0 to 1, and to do that, we can simply say occlusion total divided by equals float SSAO sample count. We do have to explicitly cast this to a float because it is an integer, and shaders are picky about that. And lastly, instead of writing nonsense to our GL underscore frag color, we can say GL underscore frag color equals a vector 3 of occlusion total on the red, green, and blue, and an alpha of 1. And this is going to TBH. Yes, the TBH matrix. That makes sense. Let's TBN. Oh, U underscore SSAO bias. Okay, again. When you write a lot of code without testing it, that's the sort of thing that happens. Anyway, so we've now got something that looks like kind of a more expensive and also kind of worse outline shader. So on the surface, it does look a lot like an outline shader, right? Which you could compute pretty simply using something like a Sobel kernel. But let's actually zoom in a little bit on the stairs here and take a look at what's going on. So the darkest part of the scene is indeed in the corners, and it is actually using this screen space and depth information and information about what's actually in the game world. So we have our corners being darker. We have our, like, the areas around the curved part of the step is a little bit lighter. Corners that would ordinarily generate an outline if you did just use something like a Sobel kernel are going to exhibit very little, if any at all, occlusion, because very few, if any, of the samples that we're taking are actually behind the surface in the depth buffer. There are some imperfections. If I were to zoom all the way in, we can see that there is a little bit of a noisy, like, staticky repeating pattern. And that is because we are taking a finite number of samples. We're taking 50 samples around each fragment, which is, don't get me wrong, that's definitely a lot. But it's still a finite number, and we're still going to have, like, imperfections where some fragments randomly sample more points that are occluded, and some randomly sample fewer, even though they should come out with about the same number across a flat corner like this. And there's a whole bunch of different things that you can do to mess with the input values to the shader, mess with the parameters that we set as uniforms, do things to smooth out the noise. You can apply blur effect to the shader. There's also the case of the background, and I don't know how most games would deal with this. The way that I would deal with this is to just attenuate the SSAO effect at a distance. Not too unlike what you might do with, like, fog or other lighting, shadows, that kind of thing. The reason that the background has this checker pattern on it is because we're kind of, like, hitting the limits of, like, there's nothing here. The depth buffer is 1. When you reconstruct position from depth, you kind of, like, you get a view space position that's basically sitting on the far clipping plane, and at that distance, the floating point noise is kicking in, and, like, our SSAO bias is, like, giving us results that are all over the place. By the way, what exactly this is for, I did kind of just gloss over this. You might recognize this sort of thing from, we used it in shadow mapping so that we didn't get weird self shadows and shadow acne and that kind of thing. We're using it here for a similar purpose so that we don't get results, like, you don't occasionally get flat surfaces that are, like, self-occluding themselves. I found that it's not really as important in SSAO as it is in shadow mapping, but all the sources that I've read about SSAO did include it, so I'm going to include it also. Anyway, now I think the last thing I'll do before ending it off is actually applying this to the scene. So, there's a couple of different ways you can do this. If you have a greater post-processing stack with other post-processing effects that you are doing in your scene, you might just want to slot that in there and, like, multiply the SSAO ambient occlusion value by the output color, something like that. I am just going to use a blend mode, so I'm going to draw the SSAO surf main, which is just the scene's diffuse color information, or the scene's, like, base color information. I think it includes lighting. And I'm going to GPU set blend mode extended blend mod. GPU set blend mode extended, BM destination color and BM underscore 0. This is just going to be good old multiplicative blending. And then we can draw surface, the SSAO, the actual SSAO surface. And when we're done with that, GPU set blend mode BM underscore normal. So, because our SSAO surface is just a black and white image with dark images corresponding to more occlusion, I'm just going to multiply that with the main image. And here, we are going to get a scene which has our SSAO ambient occlusion effect in the corners. So that's not bad. When I set out to do this the first time, I thought it was going to be a lot more complicated than this. However, there are a lot more ways that you can modify this and changes that you can make and performance considerations you might want to think about. And I think I was originally going to do this in this video, but I don't want this to be like an hour long. And I know that when I talk about those things, it can go on for a while. So I think I'm going to make that a third video on SSAO. Feel free to just mess around with this and experiment with it. And if you like how it looks and performs as it is, you don't have to worry about all the other stuff I'll talk about later. But if you want to see more, then you can come back next time. So, until next time, my name is Michael. I like wizards and dragons and making games. If you want the code for this, look for the GitHub repository down in the description of this video. Description is a hard word to say. I like to post videos about all kinds of stuff you can do in GameMaker, so if anything like this appeals to you, feel free to subscribe. I talk about both complicated 3D things like this and also more normal beginner GameMaker videos. I have a Patreon, so if you felt like contributing to the channel, links to that can be found in all the usual places, and if you wanted to pledge something, I definitely would appreciate it. You should all go check out Wizard Ducks and the Lost Hat, which is one of the games that I like to work on when I'm not doing YouTube stuff. Link to that Steam page can be found down below as well. I hope you all found this useful, and I will see you all later. Special thanks to Zenjamin, Zach Robinson, Squareco, Spydeye Games, Pixelated Pope, Paradox, Nykotic, Manta Ray, GameMaker, GameArt Indie, Edward Holt, DJ Gibbles, Brenton, Bokeh Dev, and Argo the Knot for supporting these videos. If you want to join the ranks of these very cool people, head on down to the Patreon page in the video description to join the fun.